In an earlier lesson, we were talking about finding fractional parts of pans of brownies. So for example, we imagine we were at a bake sale and there was 2/3 of a pan of brownies left. And this is how we showed that. Then we imagine someone came along and bought half of what was left. So how do we represent that? How do we show that in our picture? Yeah, we divided those 2/3 in half, right? We just drew a line down the middle and used a different color of shading to show that 1/2. And we thought of this as 1/2 of 2/3. So then we were trying to figure out what fraction of the pan the person bought. So what fraction is now shaded in orange? What was our strategy for figuring that out? Yeah, that was one thing we did, is we extended this line to go all the way up to the top of the pan because we wanted to know the number of equal parts in the whole pan. So how many equal parts are there? 6, yeah, I count 6 as well. So there's 6 equal parts in the whole pan of brownies. Why do we need to know that though? If we're trying to figure out what fraction of the pan is shaded in orange, what does that number of parts in the whole tell us? Yeah, it's the denominator of our fraction. So if that's the denominator, what would our numerator be? We're trying to say how much of this pan is shaded in orange. So what would the numerator be? Yeah, the number of orange parts, I agree. So how do we complete our number sentence then? 1/2 of 2/3 is equal to 2/6. Great, so you've already solved a bunch of these problems in an earlier lesson. You've already figured out all of these number sentences. And you're going to do some more of this today. You're going to end up solving more problems with models that look something like this. But then after you're done, I want you to make sure as you're working, you keep track of all your number sentences and your visual models, because I'm going to ask you to do something else. Once you have all your problems solved, I want you to do some pattern recognition. So that's one of our CT practices. And it's all about looking for ways that problems or solutions are similar or different to help us solve other related problems. So we said a pattern is something that's similar across more than one example. So in this case, you're going to have all those number sentences, and I want you to look for patterns in what's going on with the numerators and denominators. See if you can find any patterns. But here's the challenge. There's something else I want you to do. Once you've found a pattern, I want you to think about how you can explain why that pattern makes sense. Why does it work? And you can use your visual models to help you think about that. So for example, I know I heard some of us talking about how they noticed in a lot of these problems, the denominator of the answer is actually equal to the product of the other two denominators in the problem. And that does seem to be true in this case. 2 times 3 is equal to 6. So I'm not sure yet if that's a pattern that's true for all problems. That's something I want you to check on. But if it is, you decide it's a pattern, then how could you use your visual model to help you explain why that's true? Where do we see the 2, 3, and 6 in our visual model? Well, we did already say that 6 is the number of parts in the whole pan. So that's where we can see the 6. So something you might think about, though, is how did I get to those 6 parts? And did it have anything to do with the denominators of the other ones, the 2 and the 3? So to summarize, there's 3 things that I want you to do. First, you're going to finish solving the rest of your fraction of a fraction problems. Then you're going to look at all your number sentences and see if you can do any pattern recognition, find any patterns. And once you find some patterns, I want you to work with your partner to see if you can use your visual models to explain why the patterns make sense. Okay? I'm going to give you some time and we'll come back together after you've had a little time to work. I was watching and listening as you all were working, and there was some really great thinking going on. I want to share a couple of ways I heard partnerships talking about why the patterns work. So first, Jesse and Renee did decide that that pattern in the denominators was true for every problem. They did notice that the product of the two denominators in the problem was equal to the denominator of the answer all the time. So they started thinking about why that makes sense using this problem as an example. 3/4 of 2/3 is equal to 6/12. So they knew that denominator in the answer, 12, was showing the number of equal parts in the whole pan when they were done drawing their model. So they started thinking about how they got to those 12 parts. And they said, well, we started out showing 2/3 because that was our starting amount. And to do that, we had to divide the whole into 3 parts because of the thirds. And then you shade 2 of those thirds, and we'll just show that right now just to keep track of what's going on in the problem. But then they had to start thinking about 3/4 of 2/3. So they divided each of those thirds into 4 parts. So at this point they had 8 parts that they were thinking about, 4 in 1/3 and 4 in the other third. But they knew they ended up with 12 parts altogether. Why is that? Can anyone explain that part of it? How'd they get to 12 parts? Yeah, so we're thinking about the number of equal parts in the whole pan, so they had to extend those lines up to make sure they were dividing that last third into 4 parts as well. So that's how they got to 12 parts. So let's think about that again then. So they started out dividing the pan into 3 parts because of this denominator. And then they divided each of those 3 parts into 4 parts because of this denominator. And so they ended up with 4 parts in each of the 3/3, which is 4 times 3, 12 parts altogether. That's why that pattern makes sense. And then I heard another partnership talking about a different pattern they noticed. So not only is this true for the denominators, they also noticed in all the problems the numerator of the answer is equal to the product of the numerators in the other 2 fractions. So they explained that using similar reasoning with their drawing too. Let's use the same example. So they know that 6 represents the number of parts that are shaded orange when they're done with their model. So they were thinking about the shading. And they know that they started out by shading 2/3 because of this numerator. So at first they had 2 shaded parts. And then after they had divided those thirds into 4ths, they knew they only had to shade 3 out of 4 in each of those parts because of this numerator. So that's why they ended up with 6 orange parts altogether, because they were shading 3 in each of their 2/3. 3 times 2 is 6. So that's why those patterns make sense. So here's one more thing to think about. Do we think these patterns would be true for any problem? We're pretty sure they're true for all the problems we worked on, but would they be true for any problem? I think so, because we were able to explain it with our drawings, and even though when we made new drawings for a new problem, we would use different numbers, the process is the same. So I think they're going to continue to hold. So the cool thing about that is if we're convinced the pattern always works, we don't have to draw a model every time. We can just multiply. It's kind of like a shortcut. So it's always okay to draw a model if it helps you think about a problem. But sometimes it can be really useful to have those shortcuts too. And a really nice way to find those shortcuts is to use our CT practice, pattern recognition.